water has a density of about 1 gram per cubic centimeter. So gold has a density of twice that. Silver, on the other hand, has a density which is about 10 grams per cubic centimeter. And iron, so I'm using chemical symbols as subscripts, iron comes in at about 8 grams per cubic centimeter. And people who are sitting here and can see the whiteboard will have this as a reminder. But for those of you who are watching on Zoom,
Look, they can see, Charlie.
yeah, but I'm going to move on.
Oh, okay.
And you guys will still be able to see it.
They'll be able to see it too.
Yeah. And
We got- we'll-
anyway, you can just remember these numbers. And of course, maybe just for completeness, I'll put down here water, which is 1 gram per cubic centimeter, because that's how the kilogram was originally defined, to be 1,000, to be 1 liter, and a liter is 1,000 cubic centimeters, and so on. And but I would also point out a kind of nice conversion factor in all these things. I'll do it right here. But a gram per cubic centimeter is the same thing as a metric ton per cubic meter. So water weighs 1 metric ton, 1,000 kilograms. That's a long ton in English system, 2,200 pounds. And so this guy will turn out to be 8 tons per cubic meter. And we're going to use that in a minute because I think it's kind of a useful number.
So a box is, that's essentially 3 by 3 by 3, weighs 8 tons.
If it's iron.
Oh, it's iron. Oh, iron.
If it's water, it only weighs 1 ton.
Yeah. Still.
Charlie, you want to throw in lead?
Uh,
It's about 10.
Yeah, that is.
It's one why people cheat. They can't afford to get all the other precious
Well, no,
metals.
we're going to talk about cheating.
Okay.
And the way to cheat, I'll give you another number while we're up here. The way to cheat is with putting silver in for gold.
Yeah.
Because they will amalgamate pretty well. And just so you know, I looked up the spot market prices a few days ago. And gold is spot price is $64 a gram. And silver is 80 cents a gram. You're used to seeing spot prices for, Troy ounces. It's terrible. A Troy ounce isn't even an ounce, a Troy ounce is more.
Well, if you live in Troy, it's fine.
The drillers are trying to build like more.
But you have to dig it up.
I see.
You have to excavate Troy in order if you're going to live there. Anyway, so you can see, and this gets me a little ahead of my story, but no problem. If you want to cheat, guy gives you gold and you add silver, and that'll get us to our story. But I wanted you to understand Archimedes' principle. And I said I got 6 stories here, but that's more stories than I can tell. Okay, all right. So I'm Charlie Holbrow. I'm going to talk to you today about Archimedes' principle, and I'm going to talk about a bunch of stories. I'm not going to talk about all of these stories, but these are the stories that came to my mind as I went along. And I'm going to start with a chestnut, a classic in the field. And it's this business of a loaded barge is in a canal lock full of scrap iron. So it's floating low in the water, and then it sinks. And the question is, does the water level in the canal change? Does it go up and does it go down? And does it rise or fall? And the principle, Archimedes' principle, we'll see, provides the answer. And I've given you the principle right up at the top. We'll show you a little later that this principle makes sense in terms of physics. But it says that a body at rest in a fluid is acted on by an upward force equal to the weight of the fluid displaced by the body. There's a lot of stuff packed into that nice little statement. One of the things I'm going to just point out now is almost a digression, but you notice it says weight. You don't have buoyancy unless you're in a gravitational field. Buoyancy is anti-gravity, if you're looking for anti-gravity. We can come back to that later, but it's kind of cool. You got no acceleration due to gravity, you got no buoyant because you have no weight. And then Archimedes principle says, well, if you don't have any, if the displaced fluid has no weight, there's no upward force. But for us, for all the cases we're going to talk about today, here we are on Earth, and there's plenty of upward force. So the barge sinks. So now I take you back to our table there, where we said that iron has a density of 8 tons per cubic meter. So just as a kind of Gedanken experiment, a thought experiment, let's imagine that we have 1 cubic meter of iron in the barge. On the barge, it's floating just fine. I'm going to neglect the weight of the barge, but the barge is floating there with this block of iron in it. How much water has to be displaced in order to float 8 tons of iron in the barge? You know, what's it?
8 cubic meter.
8 tons.
So that it's got to be 8 tons of water. And Peter got it, 8 tons of water, and that means 8 cubic meters of water. So now you throw the iron, Superman. We lift up this cubic meter of iron and we heave it over the side, and it goes to the bottom. Now, how much water is this cubic meter of iron displacing?
It's not displacing anything. Oh, you take it out.
Well, we put it in. We threw it over.
Put it into the barge.
We threw it overboard into the canal. Or we stank the barge in the canal.
So it's 1.
No, it's 1.
Yeah.
So what's happened to the 7 cubic meters?
They went to the vapor.
Well, they didn't go to the vapor, Peter, but the level must have come down. And you can actually model it kind of easily. I mean, you can say, suppose the canal lock is 3 meters long, no, 3 meters wide, 5 meters long, 2 meters deep. Then, what is it? That's 30 cubic meters. And you can figure out how much the surface level would change.
So this is the same problem of there's no barge in the canal and you have a big block of whatever, and you put it into the water and the water level rises.
And of course, this is also the problem of you get into the bathtub and you fill it too full. What's going to happen to the water? The water level rises and goes over the edge of the bathtub. Right? A lock, a canal lock is just a big bathtub for our purposes.
So what if the thing you're putting into the water floats? Like a 8-ton barge or whatever that.
Well, then, what's going to happen? How much water must it displace in order to float? So that's what a boat is for. A boat makes a hole in the water.
Or an iron boat, right?
An iron boat makes a hole, and it better make a big one, because it'll sink otherwise. And a little later, I'll show you the Nimitz supercarrier, which makes a hole of 100,000 tons of water. When it's empty. When it's full, it makes an even bigger hole. But that's the idea. That's what Archimedes is telling.
And that's why they have these lines on the side of boats to show how full it is. Right?
Yeah, I suppose. You want to know how much oil is going to leak out into your harbor. All right. So
it's kind of an ill-posed problem, because if it's floating in the canal lock, why does it sink?
well, because I've drilled a hole in the bottom.
Oh, okay. Okay. Well, it's not, it's not specified.
This is, come on, Ted, this is physics. I can do what I want.
Don't with the facts.
Okay, well, I'll show you an example. I'm gonna actually.
So you've
We're gonna
added,
have a barge and we're gonna put scrap iron in it. And we're gonna sink it.
you've added water to the barge. So some of the water that was previously being displaced because there was air is now filled, that space is now filled with water.
Just, I mean, that's a very nice way to describe it. And, I was asking an aged lady of my acquaintance, what would happen? And she looked at me, she says, well, the boat kind of makes a hole in the water. And when the boat sinks, the water rushes in and fills the hole. I thought, oh, right on, you know.
The
It's
Nobel
not,
laureate, right there.
well, it's not what Archimedes said, but then I thought it was very perceptive. And so, what do I want to do? I want to go next. And so here's our Gedanken experiment. We just did this. Okay, I got ahead of myself without showing this. But here's my cubic meter there, and there's the densities and we've gone through this. When I say here, what mass of water does the iron displace? The answer turns out to be it must displace 8 tons. What volume of water is that? That's the 8 cubic meters that Peter so accurately called. And so then I give you the case of a cube falling through the bottom of the boat and thinking, now what volume does it displace? And it's a cubic meter. So we did all that. And here's my calculation to show you how much the water level will drop. You know, so I said, suppose the lock is 5 meters long, 3 meters wide, 3 meters deep. It's an easy kind of conception that the volume of water that you displaced was the height that it rose times the area of the surface of the thing. And now, when you let the 7 cubic meters go away, it goes away by letting the water level of my model go down by about half a meter. So that's kind of the game. All right, now, so that's, as I say, our Gedanken experiment. And now I wanted to show you how to sink your own barge at home in your kitchen and see that Archimedes was right, that when you sink your barge, the water overflows. And so here's my attempt to do that. And there's a lot of, this is a 4.5-minute video that I made at home. And it only took me 14 hours.
That's about right.
Well, I'm new to the game.
That's another principle.
Yeah, I think so.
Charlie, the
Yeah.
usual ratio in video production is about 10 to 1.
Well, okay, I'm just new, so I got a little higher.
Here's an recording of-
Well, anyway, here's my canal lock. It's a graduated picture. This is all done in my house, and you see that it's convenient because it's calibrated in milliliters. So if I'm going to displace a certain amount of, if I put 100 grams of something in there, I'm going to see the displacement level change by 100 milliliters, and I want to see if that's really true. And I put some white stuff in the picture because there's graduations in cups and tablespoons on the other side. And you'll see them eventually, but they're confusing and they will get into time. Anyway, so here I am showing you that it's calibrated in milliliters. Here's my barge. It's a cut down paper cup. And here's my scrap iron, which is a bunch of coins. And so now I'm going to load the barge. And now you can see I've been editing. I've built my thing great drive. This is probably day 3 in my effort. And then here's my kitchen scale. We're checking out what the weights of these things are. And you see, I can zero it by pushing the button. I can put my barge, put my canal lock on. And you see, with some effort, that it registers about 611 grams. Because the scale is in grams, and I can zero that out, so I don't have to worry about the weight of the canal lock. We'll probably do that again. And here's my fully loaded barge, and I'm pushing the thing up the scale a little bit so you can read it. It comes in at 143 grams. Here's the canal. This canal lock. I zero it. I think I actually repeat this all again. Let me see. There, just putting the barge and scrap iron in the empty canal lock, 141 grams.
You lost 2 grams somewhere.
I know it. I wonder where they went. I think it has something to do. I think it has something to do with where I put things on the scale. It's not the scale I would choose for precision. And here I am pouring water into the canal lock. Now here's where I'm thinking. So 325 grams has gone in, add a little more, 333 grams. That's 333 milliliters of water. And now I'm gonna just go through this again, because I got to thinking about it. Well, 141 grams of barge and scrap iron. Why don't I put enough water into the canal so that the sum of the two comes out at 500? That's the top level. I mean, I'm in charge here. I can do this. And you know, and I leave out the whole episode where I put the coloring in the water to see if we could mask the stuff on the back. And so here's my 141 grams of barge and scrap iron. And now I'm going to put the canal there, and I'm going to fill it to, well, what should I fill it to?
800,
Oh, come on.
whatever.
I wanted to come out to 5. I want the sum to be 500. So I should go right. I should go.
350 some odd grams.
Yeah, 359. You're right. Well, you see. So there we go, 344, and I'm drizzling this in from with 352. How close am I going to get? We should do it. A pool. I'm about to make a pool. No. Anyway, so I got it at 362. So now when I add the barge and scrap iron, what am I going to get? 500.
Over 500.
Yeah, in fact, I'm going to get 503.
Yeah.
And there it is. So it's working fine. Now, here I'm going to sink the barge, but first I want you to see that I'll just freeze frame here for a minute, but you can see that the level is very sweet here, right? 500 on the Pyrex picture. I'm fairly happy, I think. And now I fool around a little bit, trying to get a kind of better view in, so to get the level. And I never did get that to my satisfaction.
Hold your mic up.
Yeah, it's all right. But now I'm sinking the barge, you know. I love that feeling of power. Finger comes down, it's like that picture of God's finger goes down to Adam. Anyway, notice what happens to the level of the water in the canal lock. It's gone from 500 down to, well, it looks to me, it's a little bit below 400. In fact, the markers are 50 milliliters apart. And here I am again trying to get that. Well, that's a pretty good view. And, you know, it's how much would we expect? It ought to go back to 360. What do we have? Yeah, we were at 362. But it shouldn't go back to 362. Why not?
Because you have the mass and the stuff, and you have the displacement of the.
I have the volume of the coins and a piece of cardboard. And they are still displacing some water, but not very much. I mean, it's, I felt that Archimedes has been fully justified here. Okay.
He was a principled man.
Yes. Okay. But he was a very interesting man in many ways. I don't know if, so let's see, I guess.
High school physics class would enjoy this tremendously.
Yeah.
Uh-huh.
More so if you were sitting.
I can tell you a story about that too, but anyway.
They didn't enjoy it, huh?
My granddaughter enjoyed it.
There we go.
Okay, I was happy with that. So let's see, how do I guess, I know, what's I go next? Let me go next again. Yeah, I thought I should tell you this because this is important for you to know that you can take a field trip and experience your own canal lock at the Lowell National Park. I took my grandkids, a couple of grandkids there. Well, they're now 30, so it must have been 18 years ago. It was sort of the last time they were young enough to do what grandfather wanted them to do. Anyway, we went up there and I was just fascinated. I don't know if you can see here, but these are the gates are open, so the water is flowing out of the lock. This is the lock. It's run by these lever arms, and there's a couple of people there. But when you come into the lock, there you are at the sort of bottom of the lock. And a guy comes out and he leans on his great big piece of wood and swings the gate shut. And that makes it a dam. And so now the water can't get through. The water slowly rises. And when the water has risen up, he has gone to the other end of the lock and he's leaning on this big mechanical gate. I mean, this canal is a low power canal built in 1820 and various other canals added in for another 60 years. But it's pretty fascinating. I think the whole industrial park is fascinating. Take your young kids there and show them what child labor had to do. And so I highly recommend a field trip. And,
It's better than cleaning meatpacking equipment.
Yeah, that's what I am.
well, I don't know. I'm not sure. They have you ever been to Home National Park? Because it's, where they run the actual moves. And you get some sense of the racket.
Yeah.
I mean, these people worked in all day and the dust and everything, but you use children to go in underneath the loom to make repairs where springs had broken and things and something had gone wrong because they could fit.
Charlie, just as a side, was it dangerous for the kids to do that or just because they were small?
I don't know the answer, Peter. I mean, breathing that kind of stuff is dangerous
Well, that for sure.
for everybody.
You wouldn't lose your.
No, I don't think you lost kids that way.
Yeah.
But it's interesting. Lowell was founded as the ideal community. The original concept of Lowell was to be a model industrial until they found out they could do it with immigrant labor far cheaper. And you didn't have to worry about their parents getting angry at you. And it went downhill with the rest of America's industrial 19th century. All right, I just put this question up. Instead of throwing the block into the canal, what happens if you put it out on the bank? Got a different version of the barge and canal run. So
Yes.
I see one right answer and one wrong answer.
The boat will go up, therefore the level will go down.
It's Tony, I can't hear you.
The boat is going to go up, therefore the level will go down.
I mean, that's absolutely right. And, you're not displacing 8 cubic meters anymore. And so this time, the water level is going to rise even more than when you sank it, because when you sank it, you still left a cubic meter of the iron in there. And so you only were losing 7 cubic meters of displacement. Now, if you put the iron on the shore,
The shore sinks.
eventually.
That's why the water goes up.
All right. So anyway, that's enough. That's enough of the Gedanken experiment. I think what we want to do here is talk about Archimedes himself a little bit. And it's quite interesting that he's there's a lot of portraiture of Archimedes, which is pretty interesting considering that nobody has any idea what he looked like. Those are his dates there, 287 BC to 212 BC. He lived in Syracuse, and because I lived in upstate New York all those years, I thought I'd better put in a map to show you that Syracuse is actually in Sicily. But we're a very sophisticated group, and we know this. And but he's the author of, and you'll see down here, I guess, Periton Epiplesoton Somaton, and that is basically a treatise on floating bodies.
Do you want to know how to pronounce it all the way?
Hey, come on, Tony, give me a break.
Periton epipleondon somaton.
Yeah, well, I thought I did all right.
And you guys are the
For
translation.
a guy whose entire Greek is learned by learning all the Greek alphabet to do algebra and physics. Okay, But I could recognize somatum as, you know, somatic, and that has to do with body. And so I felt very sophisticated. Okay, anyway, so I did write a treatise, and the treatise itself is a story. It's just a fascinating story. I think parts of it got translated into Latin, and so we had some. It made it through the Dark Ages in Latin in monasteries, but it was of course written originally in Greek, and in 1907 in a Turkish monastery, somebody found a parchment. I don't. Do you know the word palimpsest? The palimpsest is a so you know, in classical times, parchment was very often what you wrote on, and it lasted forever. It was very long life. But in the Middle Ages, monks looking for something to write on would take these old parchments that had this meaningless Greek all over it, and they would scrape off the Greek, and then they would write in Latin their devotional writings, and that's a palimpsest. A palimpsest is a document that has been scraped and then written over. And so, 1907, somebody found the palimpsest in a Turkish monastery and or library somewhere, and it was bought and it disappeared. It was gone for a long time. It reappeared. I don't know my exact dates, but it's only a matter of maybe 10 or 15 years ago that someone who owned it brought it to conservators and physicists and chemists, and a group of people who used infrared and ultraviolet ways to enhance the underwritten stuff. It was not scraped completely clean. You couldn't really do that. And they scraped it so they couldn't see it, but you could bring it back. And so around 2010, and again, I don't know, maybe a decade, we were able to translate this piece of, we were able to see it in Greek. Again, it was not written by Archimedes, it was somebody, some scribe had copied it. Anyway, I think one of the things that was quite surprising is it's very clear. I mean, we know he was a brilliant mathematician. He was one of the first people to find a way to calculate pi by successive approximation of a polygon to a circle, and it's beautiful stuff. And he also developed, to our surprise, he really did understand calculus. He had invented calculus more or less all by himself 2,000 years before Newton and Leibniz. It's really, it just didn't take. You need to have some kind of receptiveness to this kind of genius, or it just disappears as it did. Anyway, he's a bright guy.
Before you go on, you made an interesting offhand comment about no one really knew what Archimedes looked like, yet we have these very excellent depictions. And it relates to some research I've been doing about an upcoming talk about painting, which is that realistic painting like this didn't start until the 1400s. So in fact, you were absolutely right. This was one artist's view of what Archimedes looked like, copied by several other artists. And the only other one that's realistic is Leonardo. Or is that Leonardo or not? It looks like some of the Leonardo ones. And of course, his dates are after 1400. So interesting side observation there.
All right, so I got to tell you the story, the Archimedes story, because so he lived in Syracuse, as I said, and the ruler of Syracuse was King Hiero, I guess we would say, Hiero. This is he was the tyrant of Syracuse, which means he came to power basically by some kind of a coup, but that was almost a normal way of coming to power in a lot of these Greek cities. And he ruled for, well, let's see, I guess I think these are his birth and death dates, but he ruled for, I don't know, like 40 years. And he was, so if he was a tyrant, he was an efficient and accepted tyrant. And it's a tyrant in our meaning is got connotations that are quite ugly. And they could be ugly in those days too, but the word was not altogether that. It just meant a ruler who had probably got there by force of character. Would Trump be a tyrant? Not in my book.
No.
Okay. All right. Anyway, but Hiero was important here because Hiero was king of Syracuse. He had responsibilities, and one of his responsibilities is to be sure to placate the gods so that they treat Syracuse and the Syracusans well. And one of the ways you treated that was, of course, as always, you took something valuable to the priests, and somehow that had wonderful effect. And so part of his duties as king were he wanted to have a votive crown, a crown made that would go and be in the temple and would be to Zeus. And so you need a goldsmith to make the crown. And you need to give the goldsmith a lump of gold. I did a little modeling of what a crown might be, that comes out about 50 centimeters around, maybe 5 centimeters high, and maybe a couple millimeters thick band, and that would be quite a modest votive crown. But it's quickly a kilogram of gold. So, and a kilogram of gold, is $64,000 worth of gold in the business. So that's the kind of thing a ruler might be able to do. And so he did. He gives this, and he gets the question. And someone says, the goldsmith's cheating you. The goldsmith is, giving you back a crown that hasn't got all as much gold in it. And so one of the things you say is, well, okay, we weighed a crown. We weighed the amount of gold that we gave the goldsmith. Now we'll weigh the crown. And they weighed the same. And someone said, well, if you put silver into the crown, you could put in more silver and bring the weights up. He would know better than to bring back something that was short weighted. And Hiero looked around to his chief mathematician, so goes the story, and that was Archimedes, and said, is there some way we can find out whether the goldsmith is cheating? Archimedes went off. And as the story goes, one day he's in his bath, and here you see actually this is a German Middle Ages picture of Archimedes in his bath. Surrounding him are all kinds of things which are a little odd. Let's see. So here's a crown. That's kind of how I imagine a crown. But here's another crown. I thought they were only making one crown. And then here's a body floating in a tub of water, and and there are just all kinds of things around here that are sort of Archimedean and symbols that go along with the man. But the big one, of course, is he's in the bath, and the story is that he was in the bath. He got into the bath, and I don't, we don't know, but he got into the bath, and water slopped over the edge of the bath. And he said, Eureka! I have figured it out. And of course, he ran naked through the streets of Syracuse, shouting, Eureka, Eureka. And we have this lady who is pointing at him as he goes by. I think the Greeks were actually a lot cooler about streakers than we are. But anyway, it's a nice story. But of course, the question before us is, well, what was it that Archimedes, how is it that Archimedes' principle actually works to get us through the question of who did the goldsmith cheat? And so, but I have to tell you that the Great Seal here's a completely digressive story. The Great Seal of California has Eureka on it. And of course, and it's, here, I don't get this exactly. I mean, I think this is Perseus with the head of the Gorgon on his shield, running for governor.
There's the city of Eureka.
Oh, yes, well, that's coming up here. I'm not gonna spend a long time on it, Carl, but I'm glad you mentioned the city of Eureka. Because when I spent a year at Caltech and I got to know some graduate students over there. And there was one kid who was from Northern California. And one day I saw him kind of wandering around the library and he was mumbling, Ukiah, Ukiah, Ukiah. And I said, Paul, what's that about? And he said, well, Eureka is this city in Northern California. Ukiah is a kind of another city, kind of 100 miles away. And he said, so when I discover something and it turns out to be a flop, I go around thinking Ukiah, Ukiah, Ukiah. I missed Eureka. So you see cultural richness everywhere. It's quite wonderful. Anyway, here's how this works. And this is, I thought this would probably work better than the whiteboard.
But that was in gold country up there too, that whole
Well,
area.
well, that's why they named the town Eureka. I mean, 1849.
Logic, because they go down sea, they go pretty deep into the earth too.
Because mostly the guy that found gold didn't say Ukiah.
Yeah.
It was the deep mining. Deep mining came later. I mean, those guys were using placer mining, and they were washing away mountains to get some gold. I mean, it's really amazingly environmentally destructive. The search for gold still is. Today.
And other heavy metals that they needed to precipitate it out.
I don't know enough about that. That's why I probably never got rich. Anyway, I bring you back to the fact that gold is 20 grams per cubic centimeter and silver is 10 grams per cubic centimeter density. And here's the deal. If you get yourself a two-pan balance and put the crown on one side and a lump of gold or a equivalent piece of gold on the other side, and they balance, what do you know? Well, you know that the goldsmith at least was smart enough to, when he adulterated the crown metal, to adulterate it with enough so that you couldn't catch him this way. So here we go with my questions. What mass of silver? Suppose the hierarchy gave the goldsmith a kilogram for the crown, and the goldsmith replaced 100 grams of gold with silver. What mass of silver will he use to make the crown? This is my pedagogy. I just love to ask an obvious question.
200.
No. Come on, he's got to have them come out the same way. He's taking 100 grams of gold off. He's got to put 100 grams of silver back in. Okay, that's why I like that. All right, and so then you say to yourself, all right, what will be the volume of this silver? Well, now you can see because you just divide 100 grams by 10 grams per cubic centimeter, and you get 10 cubic centimeters. That's the volume that he's added. Well, how much will this increase the volume of the crown? Because what was the volume of gold that he took out? I didn't ask you that. See, this would be asking you to think back through and stuff, okay? But what's it's 20 grams. So if he took out 100 grams of gold, how many cubic centimeters did he take out? 5. So if he took out 5 and he added 10. And so there's the story that he's increased the volume of the crown by 5 cubic centimeters. And that's really the key perception, I think, that Archimedes had, that the volume of the crown must be bigger if you put silver in it. And now the question is, how do you measure that? How do you sort of one obvious way is, it's the bathtub way. You fill a bucket with water to a certain level and you put your lump of gold in. Or maybe put your lump of gold in and fill the bucket right up to the top level. Take your lump of gold out, put your crown in, and the water will flow over the edge. That's gotta be a pretty lousy way of doing it because 5 cubic centimeters of water will flow out. You've got surface tension, you got all kinds of things going on. It's not the way. I mean, you could still hang or crucify or whatever you do, you're cheating goldsmith, but because you're the tyrant, you don't have to worry about evidence and stuff like that. But here's, I think, the kind of essence of, we don't know if this is what Archimedes did, but I can tell you, this is what Charlie Holbrow did in Physics 31A in 1952. Yes. And it is this. You weigh these things in the buckets of water because which one is going to be buoyed up more by Archimedes' principle? Which one is going to displace more water? Which one has the larger volume? The one with silver. The one with silver. And so the crown is right there. I expect if the goldsmith has cheated, I'm going to get my 2-pan balance. It's going to, when I put buckets of water around each side, it's going to go out, it's going to tilt. And that is actually fairly precise. And in fact, was for a long time a common way of measuring densities of metals. You can use it today. I'm sure you have to do something digital, but back once a long time ago, you can do it this way. So that's presumably, I mean, that's Archimedes' principle, catching the cheating goldsmith. Now, I'm gonna, let's see. Yeah, I guess I'll talk this. I had originally planned to put this on the whiteboard. It's got a nice kind of whiteboard handicraft. You see the hand of the maker in the diagram, or you see somebody who's 87 years old and kind of unsteady, or you see somebody who's that and is trying to do this with the marker on the screen, and it's crappy. But all right, so but this is very pretty. This is, I think, a lovely argument for why Archimedes' principle has to be true. And so you imagine yourself with a tank of water. So here's my tank of water, and there's the surface of the water. And I'm not putting something in there. I'm asking you to imagine that there's something in there. I'm asking you to imagine that there's a kind of thin membrane of like a little plastic bag in there of whatever shape you choose. And it's sitting there in the middle of the water, and it's full of water. It's actually, it's like I've drawn a kind of mental shape, membrane around any shape of water you want. Well, I know that water is just sitting there. It's static. It's not moving. So what does that tell me about all the forces that act on it? They tell me that, well, I mean, what are those forces? Well, there's the pressure of the water around it, and that pressure comes from gravity. There's a little weight of this layer of water exerts a weight on the top surface. This one exerts a weight on the bottom surface, which is slightly larger than the one on the top surface, because the weight is, the pressure is growing as you go deeper into the water. And then the side pressures and all these pressures together. But there's one other thing, is that on the center of mass of the water that's in your little envelope, there's gravity. So gravity is pulling down, and you can use the lovely center of mass theorem, which says that all the forces that act on a body, that anybody that has a lot of forces acting on it, there is a point that moves as all those forces were acting there, and that's the center of mass. And so there is this point in the middle of this thing. Let's see, there we go. That has a force mg down, mass times gravity, which is equal to the weight of the water that's inside your envelope. And yet it doesn't move. Therefore, all these forces that are acting on the outside must be exerting a force on what's on the inside equal to mg upwards. That's really kind of the basic argument for Archimedes' principle, because now I say, all right, suppose I take away the water that's inside my envelope and I fill it with sand. What's the buoyant force on it? Well, I know what it is because it's the mg upward that was on the water that was inside that envelope. So if you get that, I mean, that's the kind of thing where I had a colleague who taught, at this point, he would say to the class, all right, everybody put their heads down for 3 minutes and think about this. You know, people went to sleep, but and you know, the essence of it is you say, look, I had a mass of water there and it wasn't moving. And the force on that mass of water was mg down, and the force acting on it from the outside, all the other water pressing this way and that way, must have equaled the force upward. Otherwise, they would have fallen.
So Charlie, let me ask a question here.
Please.
If I take a balloon, small balloon, which is equivalent to your, fill it with water, put it in a tank of water, just like you're doing here, so it's equivalent to this experiment.
Right.
In my mind's eye, it sinks.
Let me see. Well, what will happen, of course, is
I've never done this, but I'm just thinking
Yeah.
that it sinks.
The balloon will surely distort because there's, let's see.
Will it?
I don't know, Peter. That's it. I think after you've sunk the barge in your kitchen.
No, it'll just sit there in the water. I mean, that's how a submarine works.
Depends on the density of what the balloon is made out of.
Yeah, if it's filled with water,
Peter, a classic physics balloon.
No weight on water, no volume.
Yeah.
Right, I mean, you know, the only difference, right, I mean, if the balloon was about 3 inches thick and made of rubber, it's gonna sink.
Right.
Rubber. No.
well, no,
Made of titanium, I don't know.
made of something denser than the water.
Steel. You make them of steel and you put nuclear engines in them.
Yeah, you make a submarine.
And you control how much water is in the ballast tanks. And Archimedes takes you under the North Pole ice. And provides you with a great theme for a book called The Hunt for Red October. Okay. But it's all Archimedes, I mean, submarines are all Archimedes.
Yeah,
That's what it was.
absolutely.
Yeah, but you know, I have to think about it because I think, no, I'm confused. It's a good question. You can confuse the speaker. Thank you. But I go on.
I'll make sure he doesn't ask anymore.
I know who to ask, but we'll wait till the question. All right. So funny you should mention balloons.
Won't the balloons sink in so that it just redistributes because what you've done is you've added water to that container.
Yeah. Okay. So Mike is going to give us the answer, but you see, the thing that bothers me is the pressure. The balloon has got to reshape itself some because you got to get a pressure gradient across the balloon that matches the one in the water. I'm not seeing how that works exactly.
I thought this was an idealized physics experiment, Charlie.
What's that?
I thought this was an idealized physics experiment.
Well, Mike, I'll blow away your thesis. I'll take an empty balloon and I'll fill it up with the water in the tank so that the volume of the water doesn't change.
Oh.
Where does the balloon reside?
It stays there. That's okay. If you go down, if you take the balloon down, or you know, take whatever it is, a very light vessel, put it down inside and let it fill. It just hangs wherever you put it.
Oh, will.
Yeah.
Okay.
Water's not that compressible. I mean, you have to freeze it to really change its volume.
Well, funny you mentioned that. Okay. Anyway,
Well, for extra credits,
here, I told you.
which effect is bigger? The fact that as you go deeper into the water, You get closer to the center of the earth and gravity gets higher.
Oh, good, Ted. I like it.
Which sensor are we measuring this stuff with?
But Ted, when you get closer to the center of the earth, the water starts to boil, so you have a problem.
But the water is compressible at a certain level. So then there's a trade-off because the volume of the water gets smaller as you go down.
All right, guys, I think we have to have another meeting to settle this, yeah. All right, I'm gonna move on because you brought up balloons and just a funny thing, I was gonna bring up balloons too. So air is a fluid. And a body immersed in air is buoyed by an amount equal to the weight of the displaced fluid. Every one of us right now we're not floating because we're not displacing enough air, but we got a little buoyancy. So when you get up in the morning, you
Some
say,
people come very close.
yeah. I don't know anybody who does, Peter. One problem is that air doesn't weigh much. So you have to displace a lot of it if you want to lift something big. Another problem is that not until 1783 did anyone figure out how to displace air with something light enough, turned out to be hot air, to get you up. So that was the first traveling balloons. I wonder if I could make anyway. So we have problems. How do we solve the problems? And here's the solution. Actually, I'll offer you 3 solutions. Okay. First solution. You ask ChatGPT.
We're combining two talks here now.
Well, that's right. Okay, and ChatGPT. I said to ChatGPT, I weigh 80 kilograms. How large a balloon filled with helium would I need to float off the ground? And it replies, in order to calculate the size of a balloon, we needed to lift your weight off the ground. We need to take into account several factors. I like that. Very judicious. Such as the lifting force of helium, the weight of the balloon itself, and the weight of any additional equipment or materials. So you see, he's not using physics balloons. It's engineering balloon. He's using engineering balloons. Good. And then he says, the lifting force of helium is approximately 1 gram per liter of volume. Therefore, to lift 80 kilograms or 80,000 grams, you need at least 80,000 liters of helium. 1,000 liters is a cubic meter. Yes. So you're going to need 80 cubic meters. However, this calculation does not take into account the weight of the balloon and any other materials that would be needed. Very good warning. You want to do this. In reality, the balloon would be much larger than 80,000 liters to lift you off the ground. I don't think it has to be much larger, but then it goes off to hot air balloons, which I thought was a digression, but interesting. Because that's what you can go in air. I mean, my daughter and son-in-law went up to New Hampshire and went up in a hot air balloon. They sell you a tour, another field trip, guys. In reality, it has to be much larger, and you need typical hot air balloon can lift approximately 1,000 pounds, and you don't fill the hot air balloon with helium, you fill it with hot air. So they have to be very big. That's what I can do there. But I thought you'd like to see the ChatGPT as its responsiveness uses.
So Professor, what grade would that paper get?
I would have to give that an A. I mean, it's right on the money, and I like the judicious qualifications. I think they're very sensible. And of course, I would have to check the result. And so we can do that. We can use Archimedes' principle. When I was starting to draw a balloon and all stuff here, and then I looked at the clock and I thought, geez, I'm tired, I'm going to bed. And but here's the fact that I think many of you know or would recall from long ago, that 22.4 liters of an uncomplicated gas at 1 atmospheric pressure and 0 degrees Celsius contains 1 mole of molecules of the gas. And 1 mole has a mass which is equal to the atomic weight or the molecular weight of the gas. So 22.4 liters of hydrogen contains 2 grams of hydrogen gas, 22.4 liters of air, and I'm using a kind of averaging of air, because I know it's not a pure single gas, but it's about 28 grams. It's mostly nitrogen, so that makes sense, mostly nitrogen N2, which is 20 grams. And a mole, 22.4 liters of helium has a mass of 4 grams. So now you can see how you might get buoyancy out of this thing, because they have the same pressure. A mole of these gases in a container exerts the same pressure on the walls, even though they have much less mass if it's hydrogen helium than if it's air or carbon dioxide. Anyway, so you notice that you can, if you fill a balloon with hydrogen, suppose we have a 22.4 liter balloon, and we fill it with hydrogen, we've got 2 grams inside, and we've got 28, we've displaced 28 grams of air. We've got a lift of 26 grams. We've got a buoyancy, the difference between those two. And that's how a balloon works. You have, except now I can tell you that a cubic meter of gas, I divide that by 22.4 times 10 to the minus 3, because that's what that's 22.4 liters is 22.4 times 10 to the minus 3 cubic meters. I love metric. And so anyway, that's 45 moles. So if we said that 1 cubic meter of helium will lift 28, I'm sorry, it's 24, 28 minus 4, 24, it means 1 cubic meter will lift about 1 kilogram. And so to lift 80 kilograms, I'm going to need about 80 divided by 1.08. And ChatGPT just used 1, which is what I would do in class. So I give it full credit for doing that. And I get 74 cubic meters if I do it with a unreal, I mean, it's not that precise already. Let's call it 80 cubic meters. And that's what ChatGPT said. So yes, good ChatGPT. There's a third way. And this is one.
Charlie Chat didn't do this calculation.
Say it again. No, Chat. I don't know. Oh, no, it didn't.
Chat looked up the answer. It didn't get that. It didn't get that. It gave the answer 180. It gave the it started from 80.
Yeah.
So it
Actually, no, it
didn't do the
said
problem.
It tells you, no, it tells you that the lifting power of helium was about 1 gram per cubic, 1 gram per liter. I don't know what, but it did. I forget what. I can go back and see. Can I go back and see? 80,000. So it says the lifting force of helium is approximately 1 gram per liter of volume. And you know, and you're saying he didn't do the calculation to get to this? I think he did. He said it's 80 kilograms. And that's pretty much what I did.
Well, maybe what Michael is saying that Chat didn't do the actual calculation. Chat found a paper that had done the calculation and lifted that text from it.
Well, you know what, we call that
That's exactly right. It found many papers.
Yeah.
Yeah, and you know, and when you're teaching a physics class, your students all have a book full of this kind of information. And in fact, what you're trying to do is get them to use
your number to 72 grams instead of 80.
it would have been fine. Because it would have been, when we tried it with Craig, his son-in-law, he said, we didn't tell him what the weight was. And it made up a number, which was kind of reasonable for a male. It was a smaller number. It came out with 58, 58, came out with 58 cubic meters. it's not stupid. It has its limits, but
It's more than just finding a paper, though. It has to actually substitute the numbers. If you ask the same question with 70 kilograms or 40 kilograms, it would adjust the numbers all the way through. So it's not actually just finding text that answers the question. It knows about
that's
elements of the text.
But you have to remember, this is what the value was in 2021. What it is in 2023 may be different.
all right, guys. Anyway, so ChatGPT does it, but there's a third way of finding out how to get enough balloons, and the answer is you just go out and buy a lot of weather balloons. You fill them with helium and see what happens. Well, it's funny that Larry should mention.
There we go.
Larry, your namesake. Yeah. So this brings me to Larry Walls, who in 1982 tied 43 weather balloons, each 2.4 meters in diameter, to a lawn chair, and he took off from San Pedro, California, and he flew for 45 minutes. He went to 16,000 feet. He passed through the approach corridors to Long Beach Airport. He carried a pellet gun to shoot out balloons so that he could come down. After shooting a few balloons, he dropped the gun, so it came down rather slowly into some Long Beach power lines and blacked out the neighborhood there for 20 minutes. He was met by the troopers who were waiting for him, and later, not much later, by FAA agents for violating the airspace. I mean, he was in a protected corridor, and also he was going to be fined $4,000 because he had flown an aircraft that had not been certified as airworthy, which were the 42 balloons tied to his lawn chair.
If you got a different lawn chair, it would have been okay.
So that charge was actually dropped when they could not actually convince the judge that a lawn chair with balloons was an aircraft that had to be certified. That's airworthy. Anyway, you gotta love the story, and you know, he just went out and did it. Now, the other thing which I have to digress here because I think I found it fascinating is he was a candidate for a Darwin Award, and so you have to know about Darwin Awards. And here you can see at the top that the Darwin Awards were an idea created by Wendy Northcutt, who is down here, another good story. While she was a student at Stanford, she was majoring in molecular biology, and she got this idea and started a website where she identified and awarded what she called the Darwin Awards, and they salute the improvement of the human genome by honoring those who accidentally removed themselves from it in a spectacular manner. So I gotta love this, you know. I got into a little bit because I went out and found some more, you know. There's a mixture of urban myth. I think it's an urban myth that a prospective terrorist mailed a letter bomb with insufficient postage and then opened it when it came back to him. And it's less clear that it's a a group of guys went ice fishing, and one of them threw a stick of dynamite out onto the ice. Not legal, but it's done. And his golden retriever went and brought it back. And everybody, you know, everybody will laugh at the terrorist who blew himself up, but everybody feels sorry for
The dog.
Yeah, that's right. That's, I know. Okay, so anyway, these are so-called Darwin Award winners. Now, Larry Walls did not win one because he lived. He did not remove his genome from the pool. Although I always felt So he got an honorable mention. He got an honorable mention.
Does it say anywhere that has to be unencumbered by the thought process?
Well, so I got interested in this, you know, because I thought the first thing that I just told you, they made me laugh. And I thought, oh geez, what is that? What do you want to, you know, up to? And so she has a website, it's maintained. She got out of Stanford, she went to work, I don't know what bachelor's molecular biologists do, but she was doing some of it. But it turned out the website was making more money than she was earning. And furthermore, she wrote a book. And in fact, she's now written 5 books, and I put down here in the corner, the Darwin Awards. And it's a set of Darwin Awards. And I'm just kind of sorry to tell you. I mean, I thought this would be really great. And there are a couple ones in there funny, but after a while, it's just pathetic. Because, you know, first of all, will you be surprised to learn that 88.8% of the winners of the Darwin Award are male?
Not at all.
Of course not. They are men, or they were men. And anyway, but you read the Darwin
Wait a
Award.
minute, they identified as male, please.
Anyway, you read the Darwin Awards, and after a while, it's just tedious, because most of it is a bunch of guys who got drunk. They got drunk out of their minds, and then went and did something, you know, like, I don't know, well, the one that's probably not drunk out of his mind is the guy who was trying to check the gas in his gas tank in his car with his cigarette lighter. But the others are ones where guys just, you know, do amazingly stupid things, walk off cliff edges because they're stoned out of their heads. And after a while, it just gets,
That's cheating.
well, I don't know. Well,
Just to get the award. It's not worth it.
yeah, but I have to say that the Larry Wall story ends kind of sadly, because 12 years later, I mean, he tries to make some money off. He'd been a truck driver. He tries to make some money off his feet. I mean, it was a feat, and I quite admire it in a way. But you know, he had his problems, and 12 years later, he goes out in the woods and shoots himself. So now he should get an award, but I don't know.
You got it posthumously.
That's the only way you get it.
In general, right?
All right, so I had to tell you the story of that. But there's some follow-up, because after 1982, cluster ballooning became an extreme sport. There are people now who vie for the record altitude. Cluster ballooning. And here's something, I said, oh, this is a person. But it's a cluster balloon with about 60 balloons. And they're not weather balloons. It's kind of attractive. But here is David Blaine. Now, David Blaine is not anybody I ever knew anything about, but when I talked to people, they knew about him. He's a magician, kind of a Houdini magician. He does stunts. He puts himself underwater for way too long, and locks himself in cupboards and things like that. Well, in 2020, he made a very concerted, thoughtful effort to do cluster ballooning to maximum altitude. He was aspiring to get as high as he could. I've seen his video where he gets, in the video, it says 26,000 feet, but I've seen other Wikipedia things says 24,700 feet or 7,000 meters. And he does this with a team. And he's got designers. I mean, there's a lot of technology in this. One of the things is, as he said, he was inspired by a movie he saw a long time ago where a kid goes out on a balloon.
He was inspired by what?
A child, in a movie, the child goes,
Yeah.
on a balloon.
Oh, yeah.
I mean, there's also a pop balloon. There's, did that happen in the red balloon? I couldn't remember. I just remember the balloon going along by itself. And I didn't remember it showing anybody. But anyway, of course, in the movie, the whole house goes up.
That's the one.
Anyway, this guy is serious. I mean, he seriously wants to live after it's done. There's a whole sequence of people who are trying for the record after Larry Wall's sort of roused public attention. And several of them are never heard of again. You know, there's a Japanese guy who was spotted by the Japanese Coast Guard as he goes across the border over the Pacific, goes across the shoreline, never seen again. There's another couple that I've never seen again. There's a guy, from Stowe, Massachusetts, who goes up, and gets fined $4,000 by the FAA. David Blaine gets all the permissions. He is going up. He has got access. If he goes to Page, Arizona to do it. I put the video on YouTube up there because I couldn't stop watching it, although it is over 2 hours long. I was skipping lots of it. Well, they had a team of 6 people, and he wants to tell you what each person in the team did. But I just skipped to the end where.
How did they get down?
How does he get down? Now, that's a question you would like to know the answer to when you do it, isn't it?
The air gets less dense as you go up.
Well, that's probably why Larry Walsh only went to 16,000 feet.
So it reaches us.
Well, the balloons expand,
Right.
and weather balloons,
More
break.
complicated, right?
Yeah, so if you watch certain weather balloons, they get filled, they're only half filled.
Yeah,
You know, and they look like droopy bags.
right.
At 16,000 feet, air pressure is down by a factor and a half. And the balloon will have doubled. And so I kind of think that if, I did some numbers on Larry Walsh, and he had way too many balloons. He did not need that many balloons.
He may have been inspired by William Penney Dubois, who wrote in 1947 a novel called The 21 Balloons.
Huh. I wouldn't, my reading of Larry Walsh is that he did not read a lot of it.
It's considered a children's classic.
Well, maybe. Anyway, so here we have David Blaine, and I want you to know that David Blaine looks like he's holding the balloon, but he actually has on a harness under his shirt that with a support that runs up through his sleeve, so he can run. But you watch on the video, and the way he gets down is he's going to skydive. He has, as it turns out, there's some overhead here. So up in amongst the balloons, there is oxygen tank. Because if you're gonna go to 24,000 feet, it's nice to be able to breathe. And there's also a parachute pack, which he brings down and puts on while he's there. You know, it is kind of fun to watch him do that. And he's got a ground controller. He's got a guy who is a professional skydiver telling him, you know, put the leg strap on, put the leg strap on, you know, show it. And he's got an oximeter on his finger, and they're saying, show us your oxygen. And he's going, and they say, oh, there, that gets it up, you know, and so on. Anyway, it's quite fun. So I've given you the YouTube there, even though it's still hard. And so that brings me to pretty much where I'm gonna stop, because I would love to tell you about the Hindenburg, but I think that's gotta be another talk some other day. It's a good story, and it's got, I found out that I just wanted to know how much hydrogen was in the thing. I looked up what the mass of it was loaded, a couple hundred tons. So right away, I know you gotta have a couple hundred tons of hydrogen inside the balloon to displace a couple hundred tons of air. You know, and that's enough to get you, with a little care, you get it. And but here we might as well end up with icebergs, because it's quickie. And Archimedes works very well for that. So you got to know that the density of so here is a picture of an iceberg, and this has got to be an artist's picture, because I don't think anybody ever got such a nice picture of an iceberg of 11 below water. And but the density of water at 0 degrees C, you know, it's less than 1. That's kind of interesting, and most of you probably know this, because the maximum density of liquid water is at 4 degrees Celsius, and that's 1. That's how we defined the kilogram originally. So that water is 1 at 1 gram exactly, 1.000 at 4 degrees Celsius. And so cold water, as it goes towards the freezing point, is actually lighter than water at 4 degrees, and therefore it floats. And that's why ice forms on the surface of ponds and on the ocean on the surface of the ocean. Most liquids do not do that.
And in your glass, when you put ice in it,
Yeah, that's right. But now the question that Peter raises is, what fraction of the ice cube is below the surface of the glass?
Not that much.
But that's, and that's also, sort of, I don't know, this folklore, or, you know, high school science, they say 90%. 90% of an iceberg is out of sight, and that's why we always talk about hidden, you know, only the tip of the iceberg means you see 10%. And so you have to know that the density of cold seawater is 1.025 grams, and the density of ice at 0 degrees is 0.918. I think, I don't know if that's sea ice, I hope it, I don't care. But the whole idea is that the density of cold seawater times the volume of cold seawater, here's Archimedes, is equal to the density of the iceberg times the volume of the iceberg. That says the mass of the two things. The displaced mass of water is equal to the mass of the iceberg. And you can just do a little algebra and see that the ratio of the volume of cold seawater to the volume of the iceberg is just equal to the density of the iceberg over the density of cold seawater. It's out 0.896. Let's call it 90. Okay. So folk wisdom didn't let me down.
Good.
All right, good place for me to stop. Okay, and I'll say the Hindenburg for later. I think it's kind of neat to see a picture of the Hindenburg with its swastika over New York City, which was indeed the case in 1936 and 37. Wow. Wow. But then, of course, it ended badly.
What you want to have with the Hindenburg, if you've ever heard it, there's the recording. I think it's Edward R. Murrow there.
Yeah.
When the Hindenburg went down, and it brings you to your knees.
Very many people died.
35 people died.
Out of how many?
About 70. Oh. Well, actually, no, that's not true. It had a passenger capacity of 72. Yeah, I had 72 births. It had a crew of about 50. And I think 35 people died. 34 of them were passengers. One person who was like a grounds crew, you know, that was trying to dock at the time it caught fire. But that's another story then. And then I'll stop here.